Now we'll begin bridging what we've done in Unit 1, talking about modeling, transfer functions, and what we just finished up, state space modeling, to what we're going to be doing in Unit 2, talking about analysis. And we're going to start looking at what do we actually do with the models that we've been creating in Unit 1. So we'll start by looking at numeric solutions using the models that we created. So for models where we have a state space form of them, or when we have the transfer function form, we are able to solve these models or solve these sets of ordinary differential equations numerically in MATLAB or some other computer software using an ODE solver. Now for now, we're going to be concentrating on models where we have the state space form. And we're going to see how do we put those into the solver and get our results. How do we solve for those dependent variables, or specifically, how do we solve for the state variables in state space form? But the general process of numerically solving is also going to transfer over when we are talking about transfer functions. When we are using functions built into MATLAB like step or impulse like we've seen before, or when we're using Simulink, actually, in the background, it's using the same numerical processes for the state space model. So somewhere in MATLAB, it is converting behind the scenes our transfer function into a state space model and doing the numeric solution to that, and then giving us back our result that we asked for. So there's going to be three main ODE solvers, or really one that we're going to use in this class. And the ODE solvers are rather robust. We are only in this class going to be using them, well, until Unit 4, we're only going to be using them with linear systems. So ones where we can write the state equation in matrix form, that AX plus BU, and where we can write the output equation in the form of that Y equals CX plus DU. However, we can use state space form for nonlinear equations as well, as long as we have definitions for all of the derivatives of our state variables, whether they are linear or nonlinear, we can still put it into that state space form. It does not have to be put into a matrix form in order to be able to solve it. So the solvers we're talking about are great for linear systems. Pretty much any system we encounter for the main parts of this class, we can use one of the three main numeric solvers. And probably for many nonlinear systems as well, they're going to be appropriate. But here in MATLAB and other software as well are the three main solvers. Most of the time, we are going to be using ODE 4.5. And it's good for almost all the linear systems that we would encounter. And it's generally classified as a medium accuracy solver. And it should probably be our go-to when we encounter a linear system, certainly. And probably when we encounter a nonlinear system, we might want to start with this ODE 4.5. So ODE obviously stands for ordinary differential equation. The 4.5 is the type of routine and the type of accuracy it's using to solve the system of ODEs that we are handing it. Now, maybe there's a certain situation where we want to be able to solve our ODEs faster. For complicated or very large-scale systems, ODE 4.5 could be slow. If we have a million by a million system, maybe we have a million degrees of freedom. If we're talking about a dynamic system we're using finite element modeling to solve for, it could be pretty slow to solve using ODE 4.5. So another option for big systems maybe would be to use ODE 2.3, which is generally going to be lower accuracy, but in return we get a higher speed for our solution. For this class, probably we don't need to use ODE 2.3. ODE 4.5 will be sufficient for pretty much everything we're doing. And then a third possible alternative, there's lots of other choices as well built into MATLAB, but another fairly common one that could be useful is ODE 1.5s, and this is for so-called stiff matrices. So these would be ones where maybe our spring constants are very high and very little motion is taking place. Possibly ODE 1.5s is going to be a better way to solve it, because ODE 4.5 might take a very long time to be able to solve the system and just might never get us to a solution. So ODE45, 99% of the time is going to be what you're using for linear systems, but these other options do exist as well as several others if you look in the documentation. Now, I'm only going to be using ODE45 in all the examples I do, but to call these other solvers, just replace ODE45 with the name of the solver that you want to use, and the code syntax is going to be basically the same. Now, I get into the specifics of generally how these ODE solvers work in a little bit, but what are we doing? We are numerically solving our ordinary differential equation. So what we are going to be getting is the solution to it only at specific points in time. And that's different than getting a closed form algebraic solution. So like what we did at the beginning of the course where we took our ODE, we did a Laplace transform, we did some algebraic manipulation, and then we took the inverse Laplace transform and we got a nice closed form solution. We said x of t equals, and then we had an expression. And the benefit of that is that if we put in any value of t, we know automatically what our value of x is going to be because we have that function to plug it into. So it might be several exponentials added together, but we know exactly the value of x of t. That doesn't happen with the numeric solution. We only get values for, let's say, x for specific points in time, and we don't know what's happening in between. Now, we might be able to get a pretty decent guess by doing an interpolation between values that we do know, but we don't get that algebraic closed form solution. For that, we're going to be concentrating on getting closed form solutions to these types of systems in the follow-up class to this, vibrations, where we stay entirely in the time domain, and we really want to get those closed form solutions, sometimes numeric solutions, but we want an algebraic solution. Now, let's look at the anatomy of using an ODE solver. And this is fairly specific to MATLAB how we would do it. So this is a very, very condensed version of what we would do. So I actually start below where this comment is. So what we want to do first is we want to make a function, and this function's job is to create our state equation. It is going to solve for our x dots as a vector, so our x1 dot, our x2 dot, etc. So we're going to make a function. Generically, I'm just calling it here myFun, and it has to take arguments of time and x, where x is going to be our state variables, our vector of state variables. It can also contain other variables as well, but I really recommend that the function always start with t and then x and then any other variables we have. Then our function is going to define, if we're in a linear system at least, it's going to define that A matrix and that B matrix, and it's going to use those to solve for x dot, which I am calling the variable or the variable vector xd. So that's its job, and I'll explain a little bit how the ODE solver works, but it takes in generally a time, it takes in our current state, it then is going to create the derivative or the time derivative at this time and at this state, and that's what it returns. Again, in the examples, get into much more detail of how to construct this specifically in MATLAB. But this here, that is its own function. Now, how we use this is we're going to make a script file, that's what the stuff is up here, where we are going to call the function that we made in another M file. So the basic structure looks like this. We have on the output side, we're going to have timestamps, and we're going to have our state variables, our solved state variables. This will be in columns x1, x2, x3, x4, however many state variables we have. So what we do is we're going to use, in this example, I'm saying ODE 4.5, but you could put in 2.3, 1.5s as needed, but 4.5 is most common. And what we're going to do is we're going to start with this function handle at ty. This is going to tell ODE 4.5 the names of the time variable and the state variable. Here I'm using y, but it just has to be consistent with the function. So here I'm saying at ty, this is saying, okay, the first variable, that's what I'm calling time. The second variable, that is my state vector, what I'm calling it. Then the name of the function that contains your state equation. So that's whatever we called it down here, that's what we're calling. And then we're going to slot in here This is why I like this order. I'm having here t, that's the thing we're calling time, and y, the thing we're calling our state vector. So it's fine that the way I defined it down here, it was x, and then I'm using x over here. The at sign here, this function handle tells it, hey, this thing y, that's the name of my state vector right now. So that's why I'm using y over here. But we could have said x here and x here, or q and q, they just have to match. Then any other arguments that myFun or whatever your function is called takes. Oftentimes it might only take t and x and have no other variables, but maybe you want to also be able to pass it masses or spring constants or damping coefficients. So it could have a whole slew of other variable inputs that you could give it. Right, comma. So that's the first argument we give ODE45. Then the second argument, we are going to give it either a start time and a final time to run our simulation or to run our solution. So typically we would start it at time equals 0, and then we tell it how long to be running our solution. Is it 10 seconds, 60 seconds, an hour? So that's how many timestamps, or how the range of timestamps really, it's going to get our solution for. So unlike an algebraic solution where we have just a function and we can put in any value of t, it gives us an answer, this is only going to be good in the time range that we give it. And actually here you can give it not only a start time and an end time, but you can give it a whole vector of time values, and it will give you solutions at exactly those time values that you have specified. If I give it a start time and an end time, then ODE45 is going to make the decision about what times in between those to also return in this time vector t, as we'll see in the solution. And then finally, we have to tell it, at least in this simplest form of using ODE45, we have to tell it our initial conditions. So what are the initial values of all of our state variables? So we have to make sure that if we have two state variables, that this vector has two elements in it. So it would be the values of x1 and x2 at time equals 0. Here, maybe we have 4 states. So we have to define the initial conditions on x1, 2, 3, and 4. So we need as many elements there as we have states in our system. So when we run this, it's going to solve for our state variables in this matrix X, where each column of X corresponds in order to our state variables. So x1, then 2, then 3, then 4, then however many we have. Each row of X is going to correspond to a timestamp in t. So the first value in t will always be this t0, the final value in t will be tf, and then if we just give it the range, there's going to be times in between those as well. But each row of t corresponds to the values of our state variables at that corresponding time. So that's the solution for all of our state variables. Then we can implement our output equation. This is that y equals cx plus du, if we want to be using that. Since maybe we have x1, 2, 3, 4 in the physics of our solution, but we're not able to observe all of them. So this is how we can simulate having only the observed variables. So we can take our C matrix and multiply it by that x that we just got out. Now, by the way that MATLAB at least gets x comes out as this in column vectors, where each column is one of our states. To use it properly, though, I'm going to take the transpose of x. So C times transpose of x is now going to use it with the way that we have defined C. And then I'm going to transpose that solution. Plus, and then d times u, we're not in this course going to use this because the d matrix will only contain zeros for this course, but that's not going to be universally true. So there will be times where the inputs will be affecting what we are sensing or what these observables are. So in general, you can have a d times u there. I will in this course, though, generally be dropping that since again, d is going to be a matrix of zeros anyway. So out of this, y is going to then come out as columns of each of our observable. So that's the very brief rundown of how we use our numeric solver, specifically in MATLAB. And in the several examples, you'll see this implemented as one file that just defines our xdot, and then another file that's a script that's going to use ODE45 with that function file that we defined previously.